in this part we will see how to derive Euler-Lagrange equation for a functional which is function of higher order derivative of the dependent variables. Here we have taken a functional which is function of y prime, y double prime and y triple prime. Prime is corresponding to differentiation with respect to x. So, it is function of third order derivative of y with respect to x. So, we know for minimizing this functional, the first variation delta I, that should be 0. Now, we can use the chain rule to rewrite this now. We can do integration by parts for these 3 terms. Our objective is to express all the integration in terms of delta y, variation of y using integration by parts. So, first term remain as it is, second term we do integration by parts, now for the third term delta y prime, after integrating once, so this is all about our third term. Now, for fourth term, This is the domain term. Now we can write so this term and this term, if we combine, we have, let me write this as boundary term 1, boundary term 2 and boundary term 3. So we have boundary term 1, 2, 3. Now only these two integration are left, where we can see there is delta y prime and delta y double prime. So we have to do further integration by parts until we reach delta y. So this term, so this star, this term, let I am writing further integration by parts. Already there was this negative sign. So minus d dx x2 plus, sign will change in integration by parts. So that will be d2 dx2, that is first derivative of this. This will be now delta y dx. And if we say this term is double star, then that double star contribute delta y prime integration by parts and sign change d2 dx2 d dx of this quantity delta y prime dx equal to 0. Now this is again, this integral term is with respect to variation delta y. So we can combine this and this domain term. So we can write if you see this plus d2 dx2 del f del y double prime. So, we have now boundary term 4 and boundary term 5. So, we have total boundary term 1 to 5. We will take care them at the end. Now, so all boundary terms and these two domain terms we have written. Now, about this integral term where there is delta y prime. So, we have to do further integration by parts. So, this turn out to be d2 dx2 del f del y triple prime and in integration by parts this will be delta y from x1 to x2 minus d dx of this quantity delta y. This will be delta y dx equal to 0. So, this is your boundary term 6. Now, we can write there will be one delta y that I missed. So, if you combine this domain term and this domain term and if you use arbitrariness of delta y, we can write the Euler-Lagrange equation by combining these two terms minus so we have used arbitrariness of delta y to write this combined integrand to be 0, which is the governing differential equation or the Euler-Lagrange equation. So, if you see there is a pattern, we start with del f del y, then like first order derivative we derived earlier minus d dx of del f del y prime, this already we have encountered. For y double prime, this is d2 dx2 and the sign change. So, for next del f del y triple prime minus d3 dx3. So, the next will be plus d4 dx4 del f del y 4 prime. So, in this way alternatively sign got changed. So, this is you can remember in that way. So, this is the governing differential equation for minimizing a functional having higher order derivative. This is the Euler-Lagrange equation. Now, This is about the differential equation. Now, the boundary condition. So, if we see there are 6 boundary term, we will first combine the boundary term having delta y. So, if you see boundary term 1 have delta y, boundary term 3 is delta y double prime, boundary term 4 is delta y, and boundary term 6 is delta y. So, boundary term 1, boundary term 4 and boundary term 6, all of them have delta y. So, they will be combined. So, if we write, it is del f del y prime from boundary term 1 minus d dx del f del y double prime. If you see del f del y double prime plus d2 dx2 del f del y triple prime. We combine all this with delta y. So, these are all the boundary terms with delta y multiplied with delta y. So, from this boundary term we can say on x1 and x2 either y is specified or this is double prime, this term is given. So, this is the essential boundary condition, either y is specified or this term is given. So, this is one set of boundary condition. So, we can say boundary condition 1. Now, this is all the terms associated with delta y. Now, let us see the term associated with delta y prime. So, if you see boundary condition, the boundary term 2 and boundary term 5. So, if we combine this, so boundary term 2 plus boundary term 5, they all are associated with delta y prime. So, del f del y double prime, that is boundary condition 2, and boundary condition 5 is minus d dx del f del y triple prime, minus d dx multiplied with delta y prime So, this is another boundary term. So, we should not write equal to 0, it depends on if it is 0, then the boundary term contribution will be 0. Now, here on x 1 and x 2, either y prime is prescribed or this is given. So, if y prime is prescribed at both x 1 and x 2, then the contribution of this boundary term is 0, because then delta y prime is 0 at both x 1 and x 2. Now, the another boundary term. So, this is our boundary condition 2. Now, if we see, the remaining boundary term is boundary term 3. So, this is the only boundary term associated with delta y double prime. So, if we write this, so boundary term 3 says del f del y triple prime delta y double prime at x 1 x 2. So, it tells on x 1 and x 2 either y double prime is prescribed or del f del y triple prime is given. So, this is your boundary condition 3. So, we have 3 sets of boundary condition. One is either y is prescribed, that is essential boundary condition in terms of y, or this quantity is given, this is natural boundary condition corresponding to y. The second set of boundary condition can be essential boundary condition in terms of y prime, either y prime is given or this quantity is given. The third set of boundary condition, either y double prime is prescribed or this quantity is given. So, 3 set of boundary condition, one part is essential, either the essential part, essential boundary condition, or this 3 sets of natural boundary condition. So, thus we can see when we have functional having higher order derivative, then we have this governing differential equation. We have one governing differential equation for one dependent variable, where you can see there is a pattern, sign is changing alternatively. This is the governing differential equation, and because our functional is involving up to third order derivative, there are 3 set of boundary condition on y, y prime, or on y double prime, or there can be associated natural boundary condition. Now, let me explain the concepts we have learned with one example. So, we want to find the function y equal to f x which extremize this functional. So, as you can see, This functional is function of y prime and y double prime. So, corresponding Euler-Lagrange equation will be del f del y minus d dx del f del y prime plus d2 dx2 del f del y double prime equal to 0. This is the governing differential equation. The next term, if there was third order derivative, minus d3 dx3 del f del y triple prime. The sign will change alternatively. Now, here this is our f, so 16y minus 6, that is coming from this, minus d dx of 10 y prime from this, plus d2 dx2 12 y double prime, that is coming from this, equal to 0. That is 16y minus 6 minus 10y double prime plus 12y So, this is the differential equation for which y extremize this functional. Thus, we have learned how to extremize functional for different cases, like when the functional is function of two or more than one dependent variable. Also, when the functional is function of higher order derivatives of the dependent variables. Now, we will start how to derive the variational statement from the strong form, that is the given differential equation. So, this is our strong form . So, strong form can be anything, any differential equation. I am explaining variational statement taking the differential equation in this form. So, this is the differential equation we have, and these are the respective boundary conditions. Now, the weighted integral statement can be written as which is essentially we are satisfying this differential equation in integral sense, where V is variation of u. Now, we have to do integration by parts. So, this is the boundary term. The other term remain as it is, that is v f x dx. Now, here from the boundary conditions we can see that u is prescribed at 0. So, when u is prescribed, then we know the variation at that point is 0. So, v is 0 at x equal to 0, and at x equal to L the other boundary condition is prescribed, that is q. So, this will be q and the value of v at L. The other boundary term is 0 because u is prescribed at x equal to 0. Now, all this derivation is true for any arbitrary choice of v. So, this symbol is called for all. So, that means for any arbitrary choice of v. Now, if we rewrite this statement further, we can take this term on the RHS and we can write as so, we have taken this term on one side and other two term in one side. Which we can write as in some notation AUV LV for all V. Depending on the given strong form, this AUV will be different and as well as the LV. This is the general statement we will use symbolically to denote any variational statement. If you notice, the LHS is function of both U and V, whereas RHS is only function of V, that is variation. And these two are integral, these are the domain term integrated over the domain, whereas this is only this is at x equal to L, because this is the boundary term. So, this statement is called, this form is called variational statement, or weak form. In this statement, we satisfy our differential equation in integral sense. Essentially, in finite element method, we divide the given domain in various finite elements and we satisfy this variational statement in each of these element in integral sense. So, this is our variational statement. Let me explain few terminologies in abstract mathematics. Let us consider this is a operator which is taking two arguments from vector space and it is mapping to some real space. So, u comma v belong to vector space. Now, this operator is bilinear if it is linear in each of its argument. That is, suppose we have three variable u, v, w belong to that vector space and we have alpha, beta belongs to real number space. Then so, it is linear in the second argument as you can see using superposition principle. Similarly, it is linear in first argument also. So, we can tell this operator A is bilinear if both these conditions are satisfied. This should satisfy for all u, v, w belongs to vector space and for all alpha, beta belongs to R. So, we can tell this operator A bilinear if it is linear in each of its argument. Now, we can say a u comma v is symmetric if so, if you see our variational statement we have derived, So, here you can see in this AUV, if we replace u by v and v by u, the expression AUV remains same, that is a u comma v is equal to a v comma u. So, that is the notion of symmetry. If you interchange between u and v, the expression remains same. It is not necessary that in our variational statement AUV will be symmetric. It depends on the given differential equation. There is another important thing I should mention, that is LV is linear if again L is one operator, this should be true for all V belongs to vector space real number. Now, so these are the few concepts we should understand in the variational statement. Now, we will see how to get the minimization problem from variational statement. In abstract notation, we have the variational statement. The first thing is, if this two function a and L, they should be continuous. This a u comma v, this should be bilinear and symmetric. And LV should be linear. If all these conditions are satisfied, then we can write, or rather we can pose following minimization problem. Find u such that f u equal to where now, so this is our minimization problem. So, if we summarize, we have three different forms of the same problem. One is the minimization problem, minimizing some functional. Another one is strong differential equation with boundary condition. Another one is the variational statement, that is the weak form. All these are stating the same problem in different way. From minimization problem, that is minimizing functional, to strong differential equation we get using Euler-Lagrange equation. Strong differential equation to variational statement we get by multiplying the variation with the differential equation and doing integration by parts. And from variational statement we get the minimization problem if the variational statement we can write in abstract form as A u v equal to L v if A u v is bilinear and symmetric and L v is linear, then only we can get the minimization problem. Now, as I told earlier, for some differential equation it can happen that A u v is not bilinear or it is not symmetric. In that situation, minimization problem does not exist.